Okay, get a graphing calculator to start out. Get your graphing calculators. And I have yours. Look in the cabinet on the right.
This one?
Uh-huh. Okay, any idea what this function will look like? Sine x over x. Okay, we know what sine looks like, right? Okay, but what's going to happen when we put that over x? So what I want you to do is make sure your mode is in radians. Just go to your mode, put that in radians. Then we're going to type in our equation. Remember, alpha y equals, we'll get that fraction key for you. Sine x over x. Okay, now sometimes you'll see, like in your textbook or on a test, sort of like a screenshot of a calculator graph, and you'll see things like this beneath it. And that's defining the window. The first set is always the domain, and the second one is the range. So this is giving you the x min, x max, y min, y max for the viewing of the window. So let's make our calculator match those window values. Okay, so you're going to go to window, x max, x min negative 2 pi. Now when you push enter, it's going to change it to a decimal, which is fine. Max 2 pi. Right above the little caret key, right under clear. So you have to push second to get it. What would be a good scale to use if we're graphing negative 2 pi to 2 pi?
1.
1 pi? Probably not just 1, though.
2 pi.
2 pi wouldn't have any tick marks. Maybe pi over 2? Pi over 4, pi over 2? Something like that. Because just the numbers 1, 2, 3 in relation to pi really aren't that meaningful. So I'm going to do pi divided by 2 for that scale. And again, it'll change it to a decimal. Okay, y min, negative 1. Y max, 2. A good scale would either just be 1 or 0.5. Okay, now let's graph it. This looks like a bell curve that dips below, doesn't it? Okay, so it's not, I mean, just looking at that part right there, you'd say, oh, that's cosine, but it doesn't dip below the x-axis an equal amount, so it's kind of weird in that regard. I'm going to expand the x min and max just a little bit for you to see something. I'm going to go x min.
The window is just what you see on the calculator. The window is just what you see on
Yeah, it defines what you're viewing.
If it wasn't the window, wouldn't the domain be like infinite?
Exactly. Sure. You got it. Okay, so I changed my x min and max to 4 pi and negative 4 pi, just so you can see what else is going on here. Can you see that it's getting a little flatter at the ends of the graph? Okay, so it's definitely not really like a sine graph in many ways here. Here's one of my AP classes nicknamed this the Squidward graph, because they said it reminded them of when Squidward was like dancing and doing his arms. So I always think of it as the Squidward graph now, but yeah, the little arms, or whatever you want to call them, are getting flatter and flatter as they move out towards the left and the right. Okay, so what we want to examine here, we mentioned the word limits the other day. I want to examine, as I'm climbing this hill on both sides of the graph, my x values are getting closer and closer to 0. But what are my y values getting closer and closer to? Avery, can you tell? 1. Okay, here's a better way to even tell. If I change my window y scale to 0.5, now I can see that it's like hitting that 1 on the y-axis, right? So as x values are getting closer to 0, the y values are getting closer to 1. Okay, that's the concept of a limit. But can I let x be 0 in this function?
No.
No, it's undefined if x is 0. Okay, let's look at the table and notice what happens at 0. What do you see? Error, because it's undefined. So this is how we'd have to graph it on paper. We would have a graph that technically up here at 1 has a hole in it. But then to either side we can kind of imitate what we saw on the calculator. Like that. Okay, so it's getting flatter as we move out towards the ends of the graph, but technically at the top of that hill there's a hole. Now the calculator, the screen is too small to indicate that. So it's a little misleading if we just look at this graph and we say, yeah, f of 0 is 1, because technically it's not, it's undefined. So that's how we represent it on a graph, that technically just a little hole that we have to jump over that isn't defined on that graph. Okay? All right. So if I am filling in this sentence down here, the limit of this function as x approaches 0 is what? I'm asking you, what is the y value getting closer to as x gets closer to 0?
1.
And the y value is getting closer to 1. Even though it never equals 1, it is approaching 1 as we approach the top of that hill. Okay, and that's the concept of a limit. What are you approaching? Don't even care what happens when you get there. Just what are you approaching? Okay, so using f of x as our example, we can see that the existence of a limit as x approaches c, anytime you see c, just think a number, never depends on how the function may or may not be defined at that number. Okay, look at these three graphs. Do they look pretty similar to you?
Mm-hmm.
Pretty much the same, aren't they? Okay, but the functions are very different. The functions are written below. Okay, so look at this one here. This is a fraction. Can I reduce that fraction? Can I reduce x's and cancel ones? Please say no.
No.
Correct, I cannot. Okay, because, remember, I can only cancel common factors. X is not a factor of that whole numerator, nor is it a factor of the whole denominator. But can I simplify it? Yes. Any idea how? That might actually make it look worse. Thank you for throwing out an offer, though. Anybody?
Remove x from...
Can't just cancel an x because it's not a factor of the whole numerator or denominator. Can't factor in an x out of 1. Y'all are like beating around the bush. We're getting close.
Oh, a negative.
No, but thank you, and I loved the enthusiasm.
X plus 1 times x minus 1.
Oh, there we go. That numerator is a difference of 2 squares. Keep that enthusiasm for me. So the numerator is a difference of 2 squares, so it can be factored into that. Now I actually have a common factor that cancels. X minus 1's cancel. So this graph looks a whole heck of a lot like the equation y equals x plus 1, which is a line with a slope of 1 and a y-intercept of 1. That's what this looks like, right? Except notice the hole in the graph. That is created because I can't use x equals 1. If I use x equals 1 in the denominator of the function, it will be 0 in the denominator, which is undefined. So even though this reduces, I have to graph it and say, oh, but you know what? We have to skip over 1. So that's what that little hole indicates. Okay? A hole in the graph is always created from a canceled factor. A canceled factor creates a hole in the graph. Okay, so anytime something cancels, there's going to be a hole in the graph that has to represent that value that we have to hop over. Okay, but otherwise it looks like the line y equals x plus 1. All right, so let's talk about the second one. This is a piecewise function. Notice that the first part of that is identical to what we just looked at, with the clarification for everything but 1, because 1 would make it undefined. But then you have this second piece of the graph that says y equals 1 only for x equals 1. Okay, well if y is 1 when x is 1, that's just the ordered pair 1, 1. Which is that dot that we see floating out in space there. Okay, so the very top function is this line with the hole in it at 1. But then it says, okay, well wait, put this little point 1, 1 on the graph. So it's just hanging out there by itself. Okay, so that's what the second graph is. Now the third graph is just straight up the line y equals x plus 1. And it has a closed dot there just to indicate, yep, there's no gap in this one. It's just a straight line, all points included. Okay? Now, let's go back to all three of these. And I want to examine the limit as x approaches 1. And I'm going to call it f of x, although all of these technically have a different name. But we're going to find the limit in all three of them. Okay, so what am I asking you for? I'm saying go to this graph, and this is where x equals 1, right here. Okay, I'm going to go on this side of it and this side of it, and I'm going to come in where those x coordinates are closer to 1. What are the y coordinates approaching?
2.
2. The limit is 2. Okay, let's do the same thing on this one. This is where x equals 2. I'm sorry, x equals 1. And I'm coming in on both pieces of this graph, and x is getting closer and closer to 1, but what is y getting closer and closer to?
2.
2. Even though I have this point 1, 1 down here. Right here, as I come in, the y values are getting closer to 2. Okay, on this graph, as I come in and the x values are getting closer to 1, what is y approaching?
2.
2. Every single one of these has a limit of 2, even though they are slightly different graphs. Okay, so the limit is only asking you, what are you getting closer to? Yes? If it's not open, if it's closed, you mean? Because even though this dot is included, what I'm looking for is, as I get closer, what is y getting closer to?
As x is getting to 1.
As x is getting closer to 1, y is getting closer to 2. Whether it equals 2 when we get there or not is irrelevant. We're just examining what we're getting closer to.
So A and C are the same thing.
They're all three the same limit. All three of them. Even though this dot is down here. Now, I would say f of 1 is 1. In this graph. Actually, it should be g, but whatever. But the limit approaching 1 is still 2. Because as I come in closer and closer towards x equals 1, y is getting closer to 2. Even though it doesn't equal 2 when I get there. And that's the confusing part about limits. Like, yeah, but it equals 1 down here. What are we getting closer to up there on the graph? Okay? All right, stop me if you have more questions. All right, next page. a whole bunch of confusing stuff. The first two I'm going to explain, and then these we'll kind of encounter as we go along. Okay. The limit as x approaches c, remember I said think of c as just a number, of k equals k. All right, let's take a look at that. What if I wanted the limit as x approaches 3 of 5? Okay, this is my function. What is the graph y equals 5? The graph of y equals 5, a horizontal line, right? Okay, so I've got 1, 2, 3, 4, 5. There's y equals 5. Okay, let's say that I went over to x equals 1, 2, 3. I have a point right there. As I come in closer and closer to where x equals 3, what is y approaching? 5. It's not even approaching it. It is 5. Everywhere. So no matter where I go on this line, no matter what I approach, isn't y always going to be 5? Yeah. So the limit would be 5. So that's what that means. Looks a little confusing, but it's really kind of a simple concept. Okay, let's look at a graph for this next one. The limit of x as x approaches c is c. Okay, the limit as x approaches, I used 2 in my example down there, of x. That's what I'm looking for. Okay, remember, this is the function. So what is the function y equals x?
It's just
Yep, that line that cuts straight through the middle of quadrants 1 and 3, slope of 1, y-intercept 0. Here is my graph of y equals x. Okay, so if I am over here at 2, what is that ordered pair on the graph?
2,
2, 2. So as x approaches 2, what is y approaching?
2.
2. So whatever I'm approaching, that's always going to be the limit on that line. Okay, so that's what that means.
1, 1 also be a limit?
When 1 is on it, 5, 5, yeah. So if I approach 1, the limit's 1. Okay. All right, so the rest of these are like, okay, if you have two functions and you want their limit, then you can find the limit separately and add them. If you have two functions and you want the limit and they're subtracted, you can find the limit separately and subtract them. Same with multiplication, division, a coefficient, and exponent. So these will kind of encounter as we get to them. So we'll sort of worry about those later. Okay. The very first thing that we want to try when we are given a limit situation is to just plug the number in. Just like this one, like if I plug 2 into that function, that's the limit. If I plug 3 into that function, well, there is no x there. That's the limit. Okay, so if I have a graph or a function and I want a limit, the first thing I'm going to try is, well, can I just plug 2 in? And then my y value is the limit. Now, why didn't we start with that before? Because plugging 1 into all of these back here were undefined. Okay, so if it says find the limit by substitution, it means, hey, plug that number in, that y value is going to be your limit. So that's all we're going to do. So it becomes almost like an Algebra 1 problem. 2 squared plus 5 times 2 plus 6 over 2 plus 2. And that's not undefined, is it? That's a 4 in the denominator. I can have 4 down there all day long. Okay, that's 4 plus 6 is 10, plus another 10 is 20, over 4 is 5. So if 5 is my y value when I plug in 2, then that's my limit. I don't have to do anything fancy because it wasn't undefined. All day long if it's not undefined. Okay? All right, so the next one, yeah, you hope for those problems. Find the limit by substitution. Can I plug negative 2 in here?
Yes.
It is very
Yeah, we're going to add 3 to it.
Yeah.
So it's going to be okay, isn't it?
So just be square root of 1.
I know what y'all were thinking. That you said no. You were like, I can't have a negative under the square root, which is true. That's imaginary. But that plus 3 is going to take care of it. Now, if it was just square root of x, then no, I couldn't sub in a negative 2. It would be undefined. Okay, and what is the square root of 1? 1. What the heck? Limit as x approaches c? It's just going to be 2c minus 5. It's a c. So it just means some generic number c. And without you telling me more about what c equals, that's all I can do with it.
So that's the answer.
That's it. Yep. Okay, but they're not all going to stay that easy, right? Okay, determine the limit as x approaches 0 of tangent x over x graphically. That means we're going to look at our calculator. And analytically, which means we're going to do some algebra. Can I just sub in 0?
No.
No. Okay, so we got to do some work. All right, well, let's take care of the easy part first. Let's take care of graphically. So let's graph this. And let's see what it looks like. Just change your sign to tangent there. Oh, up, and then they flip. Okay, that's kind of cool. Never know what you're getting with these. All right, so I want the limit as x approaches 0. Remember, I set this scale to 1/2. So this is 1/2 and this is 1. So as x is approaching 0, what is y approaching?
1.
Appears to be 1. Okay, so I would say the limit as x approaches 0 of tangent x over x is 1. Okay, so graphically, that's it, we're done. Now let's see how we can justify that algebraically. Okay, what if I changed tangent to sine over cosine?
So when we do these limits, it's whatever y is approaching, right?
Say that one more time.
It's whatever y is approaching.
Exactly. Your answer to the limit is what y is approaching.
And
Always.
why was it just like limit of x equals 3? Is this like going to be equaling y?
Because that graph has no undefined value at that number, so then we're just going to plug it in to find out what y is approaching. What y is approaching is what y equals on those. But I can't sub in 0 to this one. So I can't just say, well, plug it in. Okay, it's undefined. It might still have a limit. Okay, how can I simplify this? Let's think of that as x over 1. Do keep, change, flip, or simplify. What are you going to get?
What do you multiply by?
Okay, sine x over x cosine x.
So it'll be sine x all over cosine x squared.
Okay, but it's not cosine x squared. I'm glad that you said that. I would write it like this so that you don't make the mistake of making it x squared. It's just cosine x times x. It's not cosine of x times x. Okay? All right, so that looks harder. Now what are we going to do? Well, ignore the cosine. Don't we know what that looks like? The Squidward graph? Okay, so what I'm going to do is rewrite this as sine x over x times 1 over cosine. Is everybody okay with that fraction being the product of those two? Yes, ma'am.
So every time you solve it algebraically, you have to write the limit x, the little arrow, and what the number is every time.
Okay, so what I'm going to do next is use this that said, okay, well, if I want the product of two limits, I'm just going to take each limit and multiply them. So basically, I'm going to split this into limit of sine x over x times limit of 1 over cosine x. So instead of doing the limit of that product, I did the product of two limits. Okay, so I'm going to deal with this limit, I'm going to deal with that limit, and then I'll just multiply those two answers together. We know that one already. That was this graph here, and as I approached 0, what was the limit?
1.
Okay, ladies, stop being rude. All right, so this is 1. I know that limit already.
So to find these, would you always have to put it in your calculator?
If you don't know them, you can. Now, but remember what I said on this next one, what I say we try first. Sub it in. I can't sub it in here. There's a 0 in there, it's undefined. Can I sub in here?
I don't know what cosine is.
Oh, don't you touch that calculator. Let's think. Oh, you cheated. All right, look at a unit circle. Where is 0?
360.
Yep, same place as 360, far right. What's the ordered pair there? But what's the ordered pair? 1, 0. All right, on the unit circle, is this cosine or sine? Cosine. And this is sine. So that's cosine of 0, that's sine of 0. And what is cosine? 1.
So it's 1.
So I can sub this in. Okay, so this one becomes 1 times limit as x approaches 0 of 1 over cosine 0. But cosine 0 is just 1. And 1 over 1 is 1. So all of this is 1, and 1 times 1 is 1. Which is what we found on our graph. But that algebraically supports it. That looks hard, doesn't it?
I got lost.
How did you find one for the first sentence if you just put
For this one, because that one is our friend back here. Well, now we do know it. Now we know it.
So
Okay.
we just basically plugged in 0 for the x.
For this one, we just tried substitution because I don't really know what, well, actually I do know what that graph looks like. That's the graph of secant. So if you knew what secant looked like, you could think of the limit. I didn't really remember that. So I just thought of, oh, cosine 0, I can find that. Here's where 0 is. Here's the ordered pair. Cosine is the x-coordinate. Sine is the y-coordinate. So cosine of x is just 1. 1 over 1 is 1.
Okay.
Okay. Any questions? Okay. All right. So sometimes substitution doesn't work, which we've already seen. So these are some problems, these next two, that we're going to try to get around that some other way. Hint, we're going to factor. All right, so limit as x approaches 2 of x squared minus 4 over x minus 2. I cannot cancel and slash out x's because I can't factor an x out of that whole numerator. I can't factor an x out of the denominator. But the numerator does factor into what? Yep. It's a difference of 2 squares. X plus 2, x minus 2 over x minus 2. Now I have something that cancels. Common factor. Okay, so if I graphed this function, I would have a hole at 2. All right, but I'm just trying to find the limit. So I'm going to reduce this to the limit of x plus 2. Now I can sub in. And so it becomes 2 plus 2, which is 4. So if I were to graph it and find the limit approaching 2, it should be 4. Okay. All right. Any suggestions on this next one? Factor out the x's. How many x's would you factor out? 2, absolutely. I have a common factor everywhere of x squared. So I'm going to bring out x squared, 3x squared plus 7. I'm going to bring out x squared down here, 5x cubed minus 12. Common factors cancel. Where would this graph have a hole?
X.
What makes that 0? What makes x squared be 0? X equals 0. There will be a hole at 0. Okay. Now we can plug in 0. So it just becomes 3, 0 squared plus 7, 5, 0 cubed minus 12. And what does that give you?
7 over negative 12.
7 over negative 12. And I like to put my negative out front or up top so it doesn't get lost. It's not wrong if you leave it on the bottom. It's just easy to miss. Question? All right, and then sometimes we just have to throw in the towel and say, okay, fine, there's not a limit. Okay, and this next one is an example of when that happens. Do you remember how to factor a difference of 2 cubes? Something that we use so very seldom. I'm going to assume you didn't remember, and I'll put it here. This difference of 2 cubes factors into this right here. Okay, so we're going to change this to be the limit as x approaches 2 of x minus 1, x squared plus x plus 1. Those are the factors over x minus 2. Now, why did I even bother factoring? Because I can't just sub in 2. If I sub in 2, I get 0 in the denominator. I factored it, I tried, I gave it a good effort, but did anything cancel?
No.
No, so I still can't sub it in. So let's look at this on our calculator and see what is going on at 2. I know I can't use 2, but I still might be approaching the same number from the left and the right. Okay, so let's see what this thing looks like. Prepare to be entertained by this one. Cubed. Oh dear. What did I do? Okay. Oh, not very entertaining, is it? It looks kind of like a cubic function, but it's been reflected. But there's a little hidden gem in this one. There's nothing at 2. What happens if you go to the table? It gives me an error. Okay, but look to the right of 2. 26, 63, 124. There are points to the right of 2. And they're big. I don't see anything to the right of 2 because they're so high. Alright, so what I'm going to do is go to my window and I want to see higher on the graph. So let's set that Y max at like 50. So maybe a good scale there would be 10 or 5.
Oh, wait, 1 second.
Okay, so all I'm doing is viewing higher because I saw in my table that there were more ordered pairs. And look at this cute little thing up here. There's more graph. So I've got this little sort of cubic looking thing here, but then I've got this sort of wonky parabola looking thing up there that is all split up because I couldn't use 2. So there had to be a break in the graph at 2. Now, if I want to see a little bit lower, because that almost looks like half a parabola on the left, I'm going to take that window and go lower on the Y min, maybe negative 20 or something, just so I can see more of that. Okay, so now that's the full graph. So I've got this little crazy looking thing here, this little wonky thing up here, all broken up because I couldn't use x equals 2. So there is a vertical asymptote at x equals 2 right there. Okay, now let's talk about the limit then. I'm going to talk about the limit on the left and the limit on the right. Okay, so if I say I'm going to look at the limit on the left, I'm going to totally ignore this piece of the graph. As x gets closer to 2, what's happening to those y values?
Negative infinity.
Negative infinity. They're just dropping lower and lower and lower and lower.
I mean, it also cuts off if you go far enough down.
That's a flaw with the calculator. It just can't make it look like it's getting any closer. Okay, if I want to examine on the right, if I want to know x is getting closer and closer to 2, what's happening to these y values?
Positive.
They're going up, 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 closer to just positive infinity. So I have a situation where there's a break at 2, where I want the limit. On the left, the y values are getting lower. On the right, the y values are getting higher. Are they approaching the same number? No. Like this one is going downward forever, this one's going upward forever. They're not approaching the same number as if I was coming in like towards the same point. Like that's not happening, is it? So on this case, we just say the limit does not exist. And that's not a Campbell abbreviation. That's like a mathematical acceptance. Like DNA means does not exist. So sometimes we just don't have a limit. It's just not approaching the same thing. Question? Uh-huh. Yeah, if you the misleading thing about the calculator is that you don't know this is here until you look at the table. And then when you see like, oh, there's more, then you need to, expand your window value. So the calculator can be misleading in some instances. Okay, next page. Have you ever seen a graph like this? Okay, this one it's a piecewise function. Why is it piecewise? Because it's a bunch of different pieces put together in one graph. And it has a name. The name of this graph is the greatest integer function. We also call it the step function for obvious reasons. Right? It looks like little stair steps. So what we're going to talk about with this graph is a right-hand and a left-hand limit. So if I want you to examine the limit from the left, I will put a little negative after the number. And that will be read the limit as x approaches c from the left. If I want to talk about the limit to the right of a number, then I will put a little plus. And it would be read the limit of f of x as x approaches c from the right. If there is no plus or minus, then that means from both the left and the right. Okay, so sometimes we just want to know about the left, sometimes we just want to know about the right, sometimes we want to know about both and compare them. Okay, let's talk about this graph just a tad bit. Let's get some ordered pairs, and let me show you where this graph comes from. Okay, because this is the definition of the greatest integer function. F of x, y, is the greatest integer less than or equal to x. That's confusing, isn't it? Y is the greatest integer less than or equal to x. What are integers first? Okay, they're whole numbers plus their opposites and 0. So if I said draw a number line, probably what you would use to label a number line is integers. Okay, not fractions, not decimals, just those plain old numbers that we would put on a number line. Okay, so let's say that I had 0. What is the greatest integer less than or equal to 0? 0, because it's equal to it, right? Okay, but what if x was 0.1? What is the biggest integer less than or equal to 0.1?
0.09.
No decimals, because we want integers. 0. Okay, let me say that again. 0 is the greatest integer less than or equal to 0.1. So it's like you're dropping back to that closest integer. So 0.1 on a number line, what's that integer right below it? 0. Okay, what if x is 0.2? What is the biggest integer less than 0.2? 0. All the way to 0.9 repeating. What's the biggest integer less than or equal to 0.9? 0. It would drop back down to 0. So all of these would go to 0 until x is 1. Then, what is the greatest integer less than or equal to 1?
1.
1.
That lies a line.
1.1.
1.
1. 1.9.
1.
1. Until you get to 2, and then it all jumps up to 2. Okay, so that's why there is a segment here. It didn't really show up, but there is a little segment right there. So I have the order pair 0, 0, 0.10, 0.20, 0.30, all the way until I get to 1, and then it jumps up here. 1.1, 1.2, 1.3, all those go to 1 until I get to 2, and then it jumps up to that next step. Okay? So that's what's called a step function. That's what this definition means. This is really the symbol we use for greatest integer function. Your calculator will graph it. It uses this int for greatest integer. And it is found in the same place that absolute value is found, which is under the math menu. Go over to number, and you'll see down number 5 is int. And that will be our step function. Oh, why does it look connected? Remember how big my window was? So if I do zoom standard, there we go.
Oh, wait, what was the integer?
Okay, I went super fast. Sorry about that. Okay, go to y equals math, over to number, and it's number 5, int. And then just put an X in there. And you'll probably have to do zoom standard to be able to really see it as a little step function. So anybody need help seeing that? Okay, so there we go. Little steps, stair steps. Okay, what we're going to do is use this graph to answer these limit questions. Okay, part A. Find the limit as x approaches 0 from the left. Okay, this is where x is 0, where my pen is. This is the left. So I am only interested in this little piece of the graph. And as I am approaching x equals 0, what is y approaching? -1. It doesn't matter that it doesn't get to -1 there. I am approaching it as I move in towards that point. Okay, part B. Find the limit as x approaches 2 from the left. Okay, this is where x is 2. This is the left. So I'm only interested in this one piece of the graph. And as x is getting closer to 2, what is y getting closer to?
1.
1. Okay,
If
then,
you did it the other way, would it be
you mean from the right? Okay, so if I did 2 from the right, that's actually question D. So let's jump down to D super quick. The limit approaching 2 from the right. Here's where x is 2. From the right, I'm concerned with this step.
the whole line?
And I'm coming in, and what is it approaching?
2.
2. So here's
That'll
x.
be the left.
This is the right.
I was thinking because you're going left.
Okay, so yes, you are moving to the left, you are coming from the right. Yeah, that can be a little confusing. Okay, let's go back and pick up C. I want the limit approaching 0 from the right. So if you're confused by that, this is what I would do. I would put my pencil down at where x is 0. I'm approaching from the right, so I am using the piece over here. So I'm coming in on this piece. X is getting closer to 0. What's y getting closer to?
0.
0 also. Okay, now let's write in this problem. What is the limit as x approaches 2 of greatest integer x.
You go both ways.
Both, yes. If I don't have a plus or minus, that means from both. Okay, so here's where x is 2. Here's on the left. Here's on the right. As I am approaching, they don't agree, do they? They're not converging on the same point. So what's my limit? Does not exist. Does not exist. So I had a limit approaching 2 from the left. I had a limit approaching 2 from the right. But just plain old approaching 2 doesn't exist because these two numbers were different. Okay?
Wait, why wasn't it not doing it on the graph with the finger thing? Missed that.
Okay, so approaching 2 on the left is here, but on the right is here.
Okay.
And as they are coming in closer to where x is 2, these y values are approaching different numbers.
Okay.
So yes, it exists from the left, it exists from the right, but not just approaching 2 because those were different. Yes, ma'am.
On C,
Mm-hmm.
we put 0 instead of 1, so like when it was approaching 0, we put 0 even though there wasn't a line, or is there a line just overlapping?
Yeah, it doesn't really show up. You might want to draw that in. There is a little segment there.
What if there wasn't a line? Is it like just
Then it would not exist. Okay, so let's say that I'll show you on the next one. Okay, so at the bottom here it says a function f of x has a limit as x approaches the number c if and only if the right hand and left hand limits exist and are equal. So in other words, the limit approaching from the left and the limit approaching from the right, if they are the same number, then we just say it's the limit approaching that number. So that's why this one didn't exist. They were not the same. Okay? All right. So look at this wonderful graph here. Definitely a piecewise. Here's the fancy equation for that piecewise. If I asked you, what is the limit approaching 0 from the left? There is no graph to the left.
So it does not exist.
That would not exist. Okay? All right, so I'm going to go through these first few with you, and then I'm going to give you time to just talk it out with a neighbor and sort of mull it over and let it gel in your brain, and then we'll compare. Okay, first one. The limit as x approaches 0 from the right. This is where x is 0. This is to the right. I am only concerned with this piece of the graph. I'm going to totally ignore the rest. So I'm on this little piece. I'm coming in where x is closer to 0. What is y approaching?
1.
1. My limit is 1. Next one, I want to approach 1 from the left. Okay, this is where x equals 1. This is to the left. I am only interested in this piece of the graph. Totally ignore everything else. So as x approaches 1, what is y approaching?
0.
0. Okay, the next one. X approaches 1 from the right. This is where x equals 1. This little thing here is just to the right. Ignore all this up here. I'm only interested in this. I am coming in to where the x's are getting closer to 1. And what is y approaching?
1.
1. Now I just want the limit approaching 1. Okay, that means from the left and from the right, they are approaching different numbers. It does not exist. And so I'm going to get your question in 1 sec. And then the last part of this, what is f of 1? What am I asking you for? Yeah, when x is 1, what is y?
Just 1.
Just 1, because that's the point that includes x equals 1.
Yep.
So that means that there's an order pair 1, 1 on the graph.
They're both circles, would it be?
If they were both open circles, it would not exist. If they were both closed circles, it would be a function.
Stage spell right.
Because then it wouldn't even be asked of you, because that's not a function to begin with, if we had overlapping closed circles. Okay, and so what was your question?
So for the second one, where it approaches 1 from the left, why do we not count that the closed dot?
Okay, good question. So she's asking, approaching 1 from the left, why is this closed dot not important when this is an open dot? Because all I'm interested in is, as I approach, what are those y values getting closer to? And on that side of the line, they are getting closer to 0. Doesn't matter that they don't equal 0 when I get there. It's just about what we're getting closer to.
Can we do the rest on our own?
Okay, yes. I want you to fill in the rest. Talk with someone, compare with someone. I'll walk around and answer questions, and then we'll compare. Hang on, let me pause my video and then I'll come around. It better still be recording. Oh, come on. Shortly. Whew. All right. Okay, so first one you told me was 1. What about limit approaching 2 from the right? 1. What about approaching 2? 1. If these are the same, then that is your limit. Or graphically, approaching 2 from the left and the right, those are both approaching the same y value of 1. But what is f of 2?
2.
It is 2, but that's okay. Doesn't affect the limit. Because there is an ordered pair 2, 2 on the graph. That little dot hanging out there by itself. Okay, what's the limit approaching 3 from the left?
2.
Okay, 3 from the right?
2.
3.
2.
What is f of 3?
2.
2. We will use a term soon. When this happens, that tells us that the graph is continuous there. Continuous. If the limit is the same from both directions, and then when you get there, f of x equals that same number, then that just means the graph goes through that point nice and smoothly with no break. But we'll examine that again soon. Okay, limit as x approaches 4 from the left.
1.
And what about 4 from the right?
Does not exist.
Yeah, there's no graph over there, so it does not exist. Okay? All right, so guys, you have the rest of the block to add these to your homework. And most of them are just looking at a graph, getting a limit. Okay, so I know it looks a little overwhelming. It's not as bad as it looks. I will have my textbook up here so you can come and check answers. Answers are also on Google Classroom. And then I'll just help as you need it. Okay? Yes. I'll come right there. Let me stop this recording and then I'll be right there.